Alright, good day to you all. So now that we're done with the basics of vector forces, we're now going to apply this on a particle. Today we're going to be discussing about equilibrium of a particle. Now, if you recall, when we say particle, essentially we start with a body or system that we generalize or idealize and reduce it to a particle, and we tend to ignore its shape and size, but take into account the forces acting on it. So what to expect? So basically, it's gonna be a short third lecture lang naman. So we're gonna be more doing problem solving, and I ask you to do the same thing then, because it'll build some muscle memory. Um, and I told you that lecture 3 will be very, very quick since most of the principal knowledge to understand the equilibrium of particles are already discussed in the previous lecture. So just to do a quick recap lang naman. Vector forces can either be solved via its scalar notation or expressed in Cartesian vector to know its components. And speaking of components, you can project it. Each force vector has its own components, like an x, y, in case of a two-dimensional plane. You can express them along the y and x axis or project them like head-to-tail method. The sum of the force resultant vector is the sum of its components, x and y, and you can write them in scalar or vector notation format, just like so. You can also do this also in 3D. For the resultant force is the summation of all its x, y, z axes. And you can show the XYZ component along its axis or project it by a head-to-tail method, just like it's shown here in my illustration. Then, of course, you can write the equation of the force vector in this particular format or in Cartesian vector. Of course, vectors doesn't only exist in forces, but also in basic physical quantities such as displacement, where we talk length and coordinates hand in hand. So if you recall yung position vector R, it's just simply the summation of the XYZ axis natin, where we can get the XYZ component by getting the difference of its final length minus its initial length. In this case, head minus tail. Then you may get the magnitude of the position vector by getting the sums of the squares of x, y, z and square root them. Do remember from our dot product notes that the relation of force vectors and position vectors are as follows. That the force vector can be the product of its magnitude and a unit vector, and the unit vector u here is equal to the position vector over its magnitude. Now, take note that this is possible when your force vector and position vector are collinear or in the same line path of action. And of course, finally, the dot product here. We just recently solved this in our previous lecture, where the dot product is the dot product of two force vectors is equal to the magnitude, the product of its magnitude and cosine theta, and it can also be written in this format, where the products of the respective components of xyz of force vector AB, and then the sum of all three. Of course, let's not forget our coordinate direction angles, especially this particular property, where the squares and the sums of cosine squared alpha, cosine squared beta, and cosine squared gamma is equal to 1 in its respective relation with its x and y forces and its magnitude. Okay, now, so when is a particle in equilibrium and what does it mean? To maintain equilibrium, it is necessary to satisfy Newton's first law of motion, which requires the resultant force acting on a particle to be equal to 0. And this condition is stated by the equation of equilibrium summation of forces, F is equal to 0. say we have a classic two-dimensional xy plane here, and we have three vector forces. They are acting on they're acting on a particle, in this case as if pulling in all directions, but they have their own respective direction relative to their axis. And recall that per force vector can be expressed in the Cartesian vector form. You can arrange it as well that you get the summation of xy components of the resultant force is equals to 0. So it means that the particle's body in equilibrium has a 0 resultant force as well as 4 force components. So to show that, it'll be equated just like so. Here we are now going to apply the equation, establishing our equation of equilibrium equation, basically. So again, the summation for resultant force here should be 0 for it to be in equilibrium. Thus, the same is true for the summation of all vectors of the force resultant. So that will be F1, F2, and F3 should be equal to 0. You can also express this in Cartesian vector form, just like so, and equate are necessary. So the sum of all xy components, you can also write this in this particular format, should be equal to 0. Now, please take note that just a reminder that the labels in bold are called force vectors, and labels in italics are magnitudes. So if we're going to write this down, that will be with an arrow, just to indicate that in handwritten format, that okay, this is a vector. And here, same ren, do not forget. In this case, for Cartesian vector form, you just leave the arrow out if you're just writing in Cartesian vector form here, but indicate that force vector 1 is a vector by indicating that there's an arrow. You put I in the hat. I'm not particularly strict about this, but at least it'll be a much more easier to be consistent about it when we're writing our equations. So same for F2. As you can see here, it holds the sign. So this is the unit vector, so you can put it this way, or you can simply just put the negative sign out here already. Okay, let me just erase that. Or better yet, let's just apply it na lang. And then F2y, and then F3. So this one is formerly plus, so I'll just eliminate that as well. So this will be F, again negative F3y j, since it's operating on the fourth quadrant. Okay, so this one here, there we go. At least, so when we're in handwritten format, if it's handwritten format, since that's basically how we deal with our exams naman, vectors should be indicated with an arrow. Magnitude, just like so, or basically scalar lang. Okay, if it's bold in text, that means this one is a vector. This one is its magnitude. Okay. All right. Next, for equilibrium of a particle, we normally encounter three kinds of supports in particular equilibrium problems. So we have the So we have the springs, the cable, and the smooth surface. Okay. So this will be very important. Just remember this formula. So for springs, they have a what you call displacement, or sometimes they're elongated, compressed, and then S is basically the distance measured from its unloaded position. Or if you're familiar with this, it's much more commonly known as the displacement basically of the spring. And we use spring in mechanical engineering or in general engineering designs for eliminate vibration, to cushion, and to act as support as well. So the parts of the formula are as follows. F is equals to Ks, or KISS, basically. So when you think about spring, you just think, okay, I know the force here. It's just a KISS, basically. So F is the force. K here is the spring constant or stiffness. And S will be the elongated plus, if it's a positive one, it's elongated. If it's compressed one, it's negative. Distance measured from its unloaded position. Okay? So there will be an initial length and then its final length. And the difference in between them would be their displacement. Okay? If it's a positive one, so it's elongated. If it's a negative one, meaning the final distance versus the initial distance is the final distance is less than that of the initial length. So just to take note lang rin, the constant K here is usually provided in a problem. I'll start first with the smooth surface. This is the most common thing that we encounter naman eh. You probably encountered this before now. Okay? So for smooth surface, you would see here a diagram here that there's a tension pulling this particular weight here. This particular weight here is touching the smooth surface here. So when we say smooth surface, meaning we can neglect friction for now, unless it's otherwise specified on our succeeding subjects. Normally we consider friction if it's especially when we're talking about design, especially where we concern about heat being generated between two physical objects. In this case, a metal and a ground surface mismo. Okay, so the force or the tension T or the force T is projected at an angle of 20 degrees from its y-axis. It's elevated at 30 degrees. The object is elevated at 30 degrees here, and right side here is the free body diagram of that object. Essentially, if you are going to draw it again, it'll look something like this. So you have your x, y, x. You have your tension. Sorry. You have your tension here. You have the weight here. Right, let me just differentiate the color properly. So I'm gonna go for black, then there we go. Okay, and now let's reflect the forces. Let's go for red. So we know that we have a tension here. This is at 20 degrees from the y-axis. We also know that we have weight here, and this happens all the time, where when an object is in contact with a smooth surface, there exists a normal force, and that is present in between the smooth surface and the object, and is always perpendicular to the surface. Okay, so we have something here. So it's something like this. And using your your theorems regarding angles, so this is 30 degrees. Basically, this is 30. You can project it this way as well. So this is the normal force. Normally, I call it Fn. That's acceptable as well, so that you can differentiate it. Tension or force, that's okay, but we will be now using practical terms such as tension of cables, tension of wire. Okay, so for this particular sake, let's try to practice using appropriate variables. Okay, now for the cable, So we have a pulley here, basically. Okay. And let's just label this T1 and T2. Actually, there's a... let me eliminate that again. There we go. So for cable, you have to assume that the weight of the cable is negligible and it cannot stretch. So that's part of our idealization of our particularization trend. And this one can support only tension or pulling forces. So as you can see here, tension or pulling forces. And this force always acts in the direction of the cable. In this case, there's a cable here. It acts on that particular direction. And then finally, and very important needle, that when you're using a cable, the force, it is subjected to a constant tension T throughout its length. So whether it's given, for example, there's a block of weight here represented as W, and there's a tension here. Let's add letters A, B, C. Since this is assumed to be an equilibrium particle, and this cable, we will neglect its weight and cannot stretch, meaning the cable or the pulley is always subjected to a constant tension T, meaning the tension at A, B, C all throughout here is equal to the weight it's carrying. Gets? Because pulleys and cables are just used to transfer forces lang. Okay? So in this case that will be TA is equals to the W. Okay. TA is equals to W. Okay? Hence why the representation here is the same variable, because whatever the tensions is being felt here, that transfers directly to the other side as well. Okay? And then from here, you can now get its respective Tx, respective Ty, and then when it comes to, and then you just use the angle here to get its respective xy components. Okay? All right. So how do we solve it? How do we analyze a particular equilibrium of a particle problems, basically? Okay, for now, this will be our rules of engagement when it comes to free body diagram. And I've been telling you guys before to practice drawing your diagram or your FPDs before, so that you know how to project where the forces are. So, for example, we have a provided problem here. There's a block being pulled with a cable, and a force F must be applied to drag this along an incline of 30 degrees. Okay? Now, we are now going to build our FBD, and this will be a requirement. If I don't see an FBD, a free body diagram in your problem sets or your quizzes, you lose a point. Okay? Now, I want you to show your forces properly where they are, expand the angles, where the normal force is, the weight, and then finally, you lay out the forces by setting your equations of equilibrium. We'll go into that later. So, first step is to draw the outline slope. Just like so, you don't have to draw it perfectly. So, just a box and a line. Siguro what's missing lang dito is the angle. Ako would add the angle. There we go. And then from here, you show all the forces involved. What are the forces involved? You know that there's a weight of the block, so you show the active and reactive forces here. So you show the weight, the tension being pulled, the tension in the cable, okay, and of course, since it's indirect, the block is sitting in a smooth surface, there's a normal force acting on it. Remember, you could put it this way as well, or basically project it as well, just like so. Okay. Normally, if there's not a lot of forces involved, you can also put it here lang naman rin. That's fine. You just have to indicate lang what angle it is. Okay? And now you identify each forces now. From here, you can now establish your equilibrium equations. You already know the drill regarding this, especially indicating what are or if the forces are positive or negative. It just shows where it's pointed at, and from here, you can now build this XY. This is just a reference. This is not pertaining to these forces, so that this is just a sample only. So recall your XY and I and J positives and negative. See? So we have the first quadrant, we have the second quadrant, we have the third quadrant, you also have the fourth quadrant here. So you apply those signs here, so from where they are. So now that we did that, we establish the XY axis in any suitable orientation. Here we are. Label all the known and unknown force magnitudes. Here we are. The directions on the diagram. And the sense of a force having an unknown magnitude can be as shown. And then now we can now set up our equations of equilibrium. Okay. At least from this example, this is referencing this. Okay. And then components are positive, they're directed along the positive axis, and negative if they are directed along the negative axis. If the solution for a force yields a negative result, it only means that its direction or sense is the reverse of that shown in the free body diagram. Okay, so just to be clear, this example is referring this. So hence why F1x minus F2x plus 3x, F1y positive, F2y positive, F3y is negative, it's going downward dito eh. Okay. Now let's try to show if it's this one naman. Okay? So basically, if we're gonna follow the rules here, essentially we already have the label here. We know that this one, usually I project the normal force just here lang rin, so that I know where it is. So this one is 30 degrees. So from here, this is my XY plane. You have two options here. You can actually tilt this by 30 degrees so that there's no angle between the normal force and the tension is in parallel with the X force. So I call this the Y and X. You can also do here the Y prime and X and then X prime. I'm just gonna do the normal one lang, so the Y and X. So let's do it here. So essentially you establish your equations of equilibrium. So x 0 such that 0 is equals to, let's start with F. It's going to the right, but it's at an angle, and we know that's 30 degrees. So we know that F cosine 30 degrees, and then we have another. So with here we have a normal force. This will be yung X. Essentially, we're gonna project it parang just like so. Wait a minute. Drawing. What else do we have? We have yung Fn. And Fn here is sine 30 degrees. Okay. It's not cooperating right with me right now. So your Fn here is sine 30 degrees. And then that's for your Fx. For your Fy, it's equals to 0. So 0 is equals to, we have positive F sine 30. Sine 30, and then you have minus W, and then minus Fn cosine 30 degrees. Why is it yielding error on my end right now? And so F sine 30 minus F cosine minus W. There we go. So that will be your equation 1 and equation 2. Okay. Now, from here, you now have two equations, which is fitting because since you have, it's not only because if it's two dimensions, because you have two unknowns as well. And usually, you're given the weight. The same process can be done with an 3D with three dimensions. So the same principle. Oh well, basically the same principle goes if we're dealing with three-dimensional forces. Okay, the information is just shown on the screen kaagad. So let me just break down that. Let me break it down for you. So the same is true if we're dealing with three-dimensional force vectors. Each force vector has its own x, y, z axis, and the summation of the resultant force is equals to 0. Forgot this is a vector, by the way, so that should be in bold. Okay. And then the summation of force vectors F1, F2, and F3 is 0. And you can express them in its Cartesian form, Cartesian vector form, to know the x, y, z appropriately. Okay, remember, pag tumawid dito, it's negative x-axis, so that's negative I. Okay, so this one has both x, y, z, so we have yung y rin as well. It's positive, as a positive rin yung z. And then summation of the resultant x, y, z component is equal to 0 as well. So here, so from here, you can establish equations now from here. So there's three equations, and usually you're given a weight pagdating dito. More often than not, there's a weight somewhere here for being pulled here. Okay, so sometimes there's a block of weight dito. Since it's 3D, so yeah. So there's a certain weight here dito, which is technically mass times acceleration due to gravity. Okay. So I'm just gonna read this out lang naman. On the free diagram, you just establish your x, y, z axis just like so. So you need to show them where they are and label them accordingly. And then the sensitive force having an unknown magnitude can be assumed. So you just label them appropriately lang naman. Okay. So for example, for dealing with F1, you label that there's an you can actually write them down along the axis, or you can simply project it. You know that there's an F1x. Okay. You know there's an F1y, and you know there's an F1z. Okay? So madalas na pino-project natin dito F1x. That's a lot better. Tignan. There we go. Same goes for F2. So we have the X force dito, F2x. We have F2y. And then we have F2z. Same for F3. So it's running on the positive x-axis rin, so magdodoble. Just use a different color na lang. This is F3x. And then magkakaroon ng F3y. And then F3z pababa. Okay. Now let's try solving problems para so that you can appreciate how to solve 2D or 3D equilibrium of particle problems. Okay. Say we have a cable here and a weight attached to a wall. Okay. Determine the tension in cables BA and BC, and so that you know what is the required tension necessary to support the 60 kilogram cylinder in figure 3-6A. So ito yan. So there's a weight here, and para may naka-attach ng cable. So you can either do this by parts, and you start where the weight is basically. So for here we have a 60 kilogram naman, and we're already shown what the FBD here for the cylinder lang and the cable ng B at point B. So in this case, basically 60 kilograms, we just have to know yung weight niya, which is 9.81. And base FBD, the weight is equals to the tension at point BD. So we can use this data to transfer yung forces na yan across BC and BA. Okay, let's start solving. So we're here to find the tension at BA and tension at BC. So we are already given this particular FBD, so that we know that the tension at BD here is 60 times 9.81. So ito yung summation of Y forces niya, and this creates a equilibrium rin. So next, first things first is withdraw our FBD. Simple lang naman. All you have to do na lang is just project it just like so. You draw your XY muna dito, and then gayahin nyo yung kung nasaan yung cable, but just project where the sense is. So just reflect yung forces, not exactly yung figure. Just like so. So in this case, we know na papunta dito yung TBC. So TBC is 45 degrees from the x-axis, and we're given a slope triangle again. So this one is TBA naman. Okay? Kasi B to A, B to C. This one, we know already this. This is TBD. This time pointing downward since the weight is pulling it downward here. Okay? From here, we write our equation of equilibrium. Finally, we're able to use na yung summation of x and y equals to 0. Okay? So we do that. So the summation of the x forces, in this case, it's positive because if it's positive, it's going to the right. If it's negative, if it's positive, pag naman sa y-axis mo, it's going up. If it's negative, so it's just going in the opposite direction. So summation of force is equals to 0. So we equate that. We start with here. TBC is going to the right. Just make sure just to reflect your x, y, z axis again, which I forgot here. So in this case, just reflect it na nandito yan. This is TBCX. This is TBCY. This is TBAX. and this TB A Y. Well, there's only one component here, so that's TBD Y. Okay, and then you write them just so. So for TBCX, that is TBC cosine 45 degrees, easy, minus TBA 4 over 5 using your slope triangle relation is equals to 0. So that's our equation 1. And for summation of forces of y naman, that will be TBC sine plus TBA 3 over 5 minus TBD, since that's the only component naman sa y niya dun, is equals to 0. From here, this is your equation number 2. So this one you have two unknowns, so you can't solve this directly. But here you have already TBT, so you can use both equations to equate and replace one another so that you can isolate one unknown muna. And that will give you, so you substitute equations 1 and 2 so that you can isolate either way. So ang ginawa ko dito is, I use it to substitute it so that I can equate it to TBA. Just like so. And then I just substitute it here. So you see here, I'm using first equation. So TBA is equals to TBC 4. Where is it? Yeah, so I isolate TBA. So that's TBC cosine 45 times 5 over 4. Since if you divide it, magiging basically TBC cosine 45. So if you divide that, that will be TBC cosine 45 divided by 4 over 5. And I just got the reciprocal ng 4 over 5. So magiging 5 over 4. So you have this. And then from here, you have the value of TBA, which you can substitute to equation 2. And since you already know what TBD is, so that's 60 times 9.81 for this example. Unless otherwise specified, I would prefer to you guys use 9.8066. I don't know why it's acting this way, but so unless it's otherwise specified, you use whatever is given here. In this case, 9.81. Or unless I specify it as 9.8066. Okay? Meters per second squared. Okay, and then from here, you just simply substitute and isolate, in this case, tension at point P to C, and you would get 475.66 newtons or 476. And then you just simply substitute the value of TBC to your first equation to get TBA at 420 newtons. If you have any questions, feel free to PM me and try to answer you as fast as I can, especially during this online session. Okay, next problem. So that's two-dimensional. Madali na lang yun eh. Kaya nyo na yun kasi parang equation, walang pinagkaiba yan sa force vectors natin eh. What about this one? We have a combination of slope triangle. This is a three-dimensional equilibrium of particle triangle. And we have a spring dito. And just so you recall, the force here acting on this y-axis is equals to Ks. So this is basically force AB. And the formula is Ks. And we're given the K here. And S is basically the final length minus the initial length. Okay, or basically the displacement. Let's read the problem. So we have a 90-pound force load. It's suspended from the hook shown below. So we have a 90-pound here. We already have the weight. Check. If the load is supported by 2 cables and a spring, so 2 cables and a spring having a stiffness of 500 pound per foot. This is pound force per foot. So we're given the 500 pound force per foot dito. Check. Determine the force in the cables and the stretch of the spring for equilibrium. So we're determining the cables here and the stretch here. So basically we're finding S. Okay? Well, technically we're also finding the force here as well. Thus KBAD lies in the XY plane and cable AC lies in the XZ plane. So the problem made it simpler for us kasi AD is just acting on lang on an XY plane and AC is acting lang sa XZ plane. Okay. So we're gonna find yung AC, AD, AB, and of course yung displacement. Okay? Malalaman natin kung elongated siya, so positive sign. Malalaman rin natin kung compressed yung spring if it's negative. But more likely than not, this is going to be elongated kasi the force is being pulled apart eh. Pero depende, tingnan natin eh. Okay, first things first is of course we draw our FBD. And of course, identify our X, Y, Z component. Never forget that. So how do we do that? So we do it step by step basically. So for you to understand this, you draw your diagram muna, your free body diagram. So here's your XYZ plane. Next up, you reflect the forces involved. You see? So there's a force AB, force AC, and force AD. Of course, the 90-pound force. And their projection relative to the axis. In this case, this is projected 30 degrees from the negative y-axis. This one, FAC, has its slope triangle, F5, 3, and 4. And then from here, you reflect the XYZ axis, just like so. You notice here, hindi ko na dinagdag kasi FAB just lies along this is FABY. And this 90-pound force lang naman. That's understood. So you just put it there lang muna. And then from here, we can now set up our equations for equilibrium. So we start force with, isa-isay natin. Let's start with X lang muna. What is the plane involved? So for X-axis, we have AD, since may X component siya, and AC. FAB, wala. So that's 0. So for FAD, X, that's simply FAD sine 30 degrees. For FACX naman, so this is FADX. This is FACX. You can put it this way rin naman para organize. Ganyan. So for FACX, okay, it's in the negative X axis. So that is just simply FAC times 4 over 5. 4 over 5. And negative siya equals to 0. That's our equation 1. FADX is simply FAD sine 30 degrees. Now, we try naman yung y-axis. Summation of y-axis equals to 0 such that we have FAB, that's good, going to the positive y-axis. And then we have 1 FADY going to the negative axis. That is FAD cosine 30 degrees. And for FAC, there's no y-axis involved, so that's 0. So we reflect the equations as such. So that will be our equation number 2. Next is z-axis. Who are we talking here? We're only involving FACZ and then of course the weight. So that's good news. So we have FAC times 3 over 5. You recall yung slope triangle rule natin, relation, minus 90 pounds because it's in the negative Z axis. So that will be our third equation. Then from here, we now solve equations accordingly. So we can start with AC since we know the weight already at 90-pound force. So we simply just transpose 90 pounds to the other side of the equation and then lipat lang natin si 3 over 5 and we will get 150 pounds. So that's one down. One down and 2 more to go. What can we solve next with AC? With knowing AC, we can now solve equation 1. So you substitute this to equation 1 and we will get 240 pounds. Then from here, we already know AD. From here, we can now solve equation 2. FAB here is just simply the, yeah, we'll get the force dito at 208 pounds. There we go. And then from there, we are left with one more problem. What is the displacement basically? What is the stretch of the spring for the equilibrium of the spring to maintain equilibrium? So recall that we have this formula where force is equals to Ks. This FAB is here. Okay, we have K at 500 pound force per feet. All that's left is the S. So we just manipulate the formula to isolate S, and we have already the difference between the final and initial already. So that's 0.416 feet. Or you can convert this much better in inches. 0.416 times 12. So that's about 4.9 or 4.99 inches or 5 inch of displacement. In this case, positive siya, so that's 5 inches of elongation to maintain equilibrium, at least for that particular cable. Questions? Okay, good. So as you can see, bulk of the work is really from understanding the given and laying it out piece by piece. You first lay out the XYZ axis, you lay out your forces involved. You don't have to draw the entire drawing here. I just need you guys to show the free body diagram. I just need you to show me where the forces are. In this case, FAB, FAC, FAD. Okay, just don't forget lang the arrow kasi those are force vectors. Okay, and then show the components. X, Y, Z, depending on where they are. The next step is you establish equilibrium. And once you're here, you're almost halfway there. Kasi from here is simply a matter of manipulation na lang ng equation. Which one would you solve first to solve, which one you would solve first to get the first unknown, and then it cascaded from, it can cascade from there. Sorry, I'll start right there. So it's just a matter of solving which particular equation so that you can solve the first unknown. Okay, and the more unknowns you solve, you'll be able to solve all the equations here. Just make sure to cancel your units properly. Do your unit analysis. The ones that tinuturo sa inyo sa thermodynamics, it's still applicable rin dito. Do your unit analysis so that you leave no room for error. Do not forget your units, by the way. Do not forget your units because we're not talking about constants lang naman dito. We're talking about variables with actual value dito. Okay? I believe this is the last problem, sample problem. So we're given a different kind of set naman. So we're given a spring, pero this time we're given a coordinate direction angle. Okay? And then we're given a coordinates basically relative to their axis. So we have a position vector problem here for one of the vectors. Okay, we not only have force vectors, we not only have a spring here, but we also have a position vector here. And we need to find AD. Okay? So let me walk through you here. So we're here to determine the tension in each. Wait lang, where's my laser pointer? So we're here to determine the tension in each cord used to support this 100 kilogram plate shown in this figure below. So we're given what else? We're given the dimensions, we're given the coordinate direction angles, and we're given the spring constant K at 1.5 kilonewton per meters. So what do? Okay, we're now given with 100 kilograms, so we just simply convert that to weight. I just used the 9.81 example here, but next time let's use the 9.8066. So you will get 980.66 or 981 newtons. 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 981 And then from here, you build your FPD again. So this is your X, your Y, your Z, and then reflect the forces accordingly. So we have AD, FAC with its coordinate direction angles, and then FAB. I separated the diagram for FAD, don't worry. And then from here, I can now express, since we're talking about 3D, sometimes it's best to convert them in Cartesian vector notation so that I can lay out where the forces are. Okay, you can write it down here as well, but you can also express it in Cartesian vector notation. Okay? Okay, but please remember to reflect where the forces are as well dito. It becomes too cumbersome lang. So if you want, you can do it by parts. So this is for force AC, these are the components. This is for force AD, these are the components. And this is for force AB. Okay? So you reflect them as such. So force AB, there is no Y, there's no Y component, there's no Z component, so only the X component. So FABI. For force AC naman, remember the CVN when using the coordinate direction angle. So we have FAC cosine alpha, FAC cosine beta, and FAC cosine gamma. Okay. So the mistake here is that I forgot to write the letters. I think they were not copied. And then sorry, this one's J. All right, this one's J, and this one's K. There we go. And then you can simplify it further by, since the angles are already given, by expressing as such, leaving only the magnitude FAC. And then for force AD, or tension at AD, we just simply, what I did was I separated them. So we have this, and remember our head to tail. So we already have the RX, RY, this RY, this is RY, and then RZ. So we know there's 2 meters here, oh, there's 1 meter, then 2 meters, then another 2 meters here. So from here, we can now establish our equation for FAD. But if you recall, there's a RAB is not equal to FAB. Okay? You have to create the equation for here. So in this case, let me show you. The relation in between them, since they are collinear, okay, they're acting on the same line of action rin naman, will be this one. Okay. So this is the relationship. So force AD, again, force AD is not directly equal to RAB. You have to go through this. So recall that F is equals to F times U. So this is the unit vector. This is the magnitude. And R is simply the components of this, head to tail. That's a lot easier. This is already given since you already know this one. This came from this. Okay. And then of course, once you know those units na, you can simply get the magnitude of the position vector R. And now you have your equation 3. So you have your equation 1, 2, 3. Then you simplify this further. Yeah, so this will be your equation 3. And now we establish first our from this particular point. For this particular point, we already know our components as well, based from this. So we now establish our equations of equilibrium. We do that by doing it one by one. We start with the summation of forces with X. Sorry, wait lang. This is a different pala. So remember that summation of all forces is equals to 0. So if we do that, the summation of all forces is equal to 0. That includes the weight, that's a force. So that's equals to the force, the summation of force vector FAO, FAB, FAC, and weight is equals to 0. So this is where uh, Cartesian vector notation comes in play, so that we can solve them algebraically properly. We could do it just like so, but we can also differentiate it per x and y and z components. So we just simply substitute. And we first, upon isolating, we will get first the FAC 813, AB 694, AD at 669. You can also solve this in Cartesian vector notation form. But units will cancel out it. So you have to equate them properly to its respective x, y, z axis. So for me, this one's a lot easier then. Here, it's a lot easier lang to show what are the x and y components are lang. Questions? So you can see, again, bulk of the work comes from actually projecting it and establishing what are your forces are. Okay? Sometimes it's okay to solve them by piece, just like what I did here, since it becomes cumbersome. Just remember to reflect your XYZ components as well. And don't forget the units. You notice here that there's no arrow here because they're not force vectors. Because we're being asked what are the forces and what are the tension. Okay, the tension. So what its quantity, what's magnitude, basically. So this is acceptable. And with that, that ends our recording for lecture 3, equations of equilibrium.